Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
大家好 Welcome to GTC Taiwan. This is a conference that is dedicated to researchers and scientists whose groundbreaking work are simply impossible with normal computers. They need a supercharged form of computer to solve the grand challenges that they're tackling. That's what this conference is about. This conference is also about the ecosystem of system makers, supercomputer makers, software developers who are creating the infrastructure to enable their work. I've got a lot of things to tell you today, so let's get started. Computing is the most important invention of humanity. It is the single most important tool that we have ever created. Over the last 25 years, the computer has advanced in performance 100,000 times. 100,000 times in 25 years, and then it stopped. Moore's Law ended. However, application demand is greater than ever. Scientists and researchers are at the brink of discovering solutions for precision medicine. They're at the brink of being able to solve weather prediction and understanding climate. We're at the brink of being able to discover the next groundbreaking material that's light and strong, or new ways of store energy. We're at the brink of discovering a way for machines to operate themselves. We're at the brink of discovering artificial intelligence. Computing demand is greater than ever. So more than ever, we need this computing performance to continue to extend. We need to extend Moore's Law. And that's the reason why so many people have jumped onto the computing approach, the computing architecture that we pioneered over 10 years ago. We call it NVIDIA GPU computing. The developers are jumping onto this platform in droves. In just the last 5 years, developers have increased by 10 times. 10 times. 850,000 developers of CUDA all around the world. The number of CUDA downloads, CUDA is NVIDIA's software architecture, computing architecture, CUDA, has been downloaded 8 million times, an increase of 5 times in the last 5 years. Incredible. The number of attendees. This is our record crowd in Taiwan. We do GTC all over the world, in Santa Clara, in Japan, in China, in Europe, in Israel, in Washington, D.C., and here. And this last year, the number of attendees grew to 25,000 people, the largest ever. This is, in fact, have become one of the largest computing developers events, 7 times in the last 5 years. If you just look at the number of computing flops that are in supercomputers all over the world, in just the last 5 years, it has increased by 15 times. That is so much faster than Moore's Law. The reason for that, of course, is that without GPUs, it is simply impossible to deliver the type of performance that is necessary in high-performance computing. It is instructive to estimate what is the gap that we would create if we didn't find a solution forward. In the last 25 years, computing has advanced and improved in performance 100,000 times, and then it stopped. So the next 10 years, if we just simply estimate the next 10 years, which is just around the corner, the next 10 years, if Moore's Law did not continue, if we do not find a path forward, applications will continue to demand more performance. In the next 10 years, application will require another 100 times more performance using historical methods. In fact, I believe in the next 10 years, computing demand will be faster than 100 times. But even if it's just 100 times, let's estimate how much computing would be missed in the world in just 10 years' time. This year, let's estimate that we ship 20 million server-class CPUs. 20 million server-class CPUs at 0.5 teraflops per CPU is 10 million teraflops. 10 million teraflops. By 2028, that will grow. The demand will be 100 times more. 100 times 10 million teraflops. 100 times 10 million teraflops is essentially 1,000 exaflops. The world does not have an exaflop supercomputer. In the year 2028, we need to ship an equivalent of 1,000 of those. Incredible amount of computing is essential to ship in just 1 year, 2028, 10 years from now. So the gap is enormous. The gap of computing demand is absolutely enormous. Just to put it in perspective, if you take the highest performance GPU we have, hey, Paul, could you hand me if you take the highest performance GPU we have, this is the Volta GPU. This is the most complex processor the world has ever created. In the year 2028, we would need to ship an equivalent of 10 million of these. 10 million. 10 million of these would be equivalent to 1,000 exaflops. Unbelievable amount of computing is missing. And that's why we need to find a solution. Today, I'm going to talk about 4 things. By the end of this presentation, I will fill the schematic. This is the only keynote from a CEO who has a schematic. Engineer keynote. This is what you get when you come to an engineer CEO's keynote. Okay, so we're going to talk about several things. We're going to talk about all of the developments in the last year as we prepare for GTC, the advances in the NVIDIA accelerated computing stack, our ecosystem consisting of applications and system partners, and I'm going to talk about 6 large markets. The singular weakness of GPU computing is this. You cannot just put a GPU, a chip, in a computer and magically it becomes faster. There is no magical rearrangement of transistors that will allow you to put something inside the computer that magically makes it go faster. If it was possible, CPU makers would be doing it right now. There are no more solutions to reorganize all of the transistors inside a CPU or even make more CPUs that will allow you to make applications go faster. We now need to optimize the entire stack. What NVIDIA's GPU computing approach pioneered was the entire stack thinking, from architecture to processor to systems, system software, APIs, libraries, and application solvers. We optimize across the entire stack, one domain at a time. One domain at a time. And it is incredibly hard work. And that's one of the reasons why it's taken us almost 10 years to get here. There are 6 vertical markets today that we have optimized and accelerated. And I want to talk to you about these markets because they're very, very large. If you're able to think across the entire stack, my voice disappeared this morning. I'm not yelling at you. I just want you to hear me. 1 second. We are family. It's okay, right? Well, I'm always so happy when I come to Taiwan. That's why I arrive early. This is the only conference I go to where I arrive 2 days early. Everybody asked me, why are you going so early? I said, I don't know. I just got to get there early. So that I could see Spencer, my son, and we can eat everything. So I already gained 10 pounds in 2 days. So good. Okay, so accelerated computing, to remember, it's really about the architecture, which we call CUDA, GPU, the design, and all of the microarchitectural innovations that go along, and the process technology that we get from TSMC, and all the packaging technology that we work with you on, advanced system memory technology, system architecture, system software, CUDA and Nickel. Nickel for connecting multiple GPUs together and getting them to cooperate and synchronizing them. Very, very complicated problem. To solvers on top, cuDNN, TensorRT, I'll talk about many of them. To the applications on top of that. Now, NAMD is for molecular dynamics, AMBER for molecular dynamics, quantum chemistry applications, so on and so forth. So many different types of applications on top. Okay? And so we optimized the entire stack. In the year 2013, you add a GPU to the CPU, you accelerate the applications by already many times. By just adding a GPU, with that entire computing stack, we can accelerate the CPU. Go forward literally 5 years. Fermi, Kepler, Maxwell, Pascal, and now Volta. 5 GPU generations later, notice every single layer of software has been innovated, from 5.0 to 9.0. The entire computing stack has been modified, improved, enhanced, new inventions, and as a result of all that hard work, we improved an application that was sitting at 1.0x in 2013 to 100x in 2018. Think about that. We took an application that was at 1.0x in 2013, you add a GPU to it, and more generations, more and more software. By 2018, we've accelerated by 100 times. Without it, the CPU would have lagged behind Moore's Law. Moore's Law would have increased naturally in the historical days, would have increased by a factor of 10 in 5 years. Factor of 10 in 5 years. But it didn't achieve that. Only 3 or 4. And yet, with the GPU, we've been able to not only accelerate by 100 times, in that last 5 years, the GPU itself, the GPU accelerated stack itself, has improved and increased by 25 times. By 25 times. What that basically says is we're now moving faster than Moore's Law. But it requires us to innovate across the entire stack. I'm going to come back to that over and over again. We're going to innovate across the entire stack, and there's so many new ideas to innovate across the entire stack. Supercharged form of computing. As in all forms of computing, as in all technologies, successful technologies ultimately does something that was impossible in the past, but it becomes super successful if it was also more cost effective. This is what a high-performance computing cluster looks like in the past, traditional. 600 dual CPU servers would consume 360,000 watts, 360 kilowatts, 360,000 watts. If it was GPU accelerated, it looks like that. Can you see that? Before? After? Did you guys see that? Did you understand it? Before? After. Okay? 30,000 quad GPU servers, 48,000 watts. 1/5 the cost, 1/7 the space, and 1/7 the power. 1/5 the cost. How is it possible? 1/5 the cost. 1/5 the cost. What a tremendous breakthrough. What a tremendous breakthrough. And that's why people tell me, the more you buy, the more you save. The more you buy, the more you save. NVIDIA's accelerated computing stack. This is the promise of the future of computing, but it requires a tremendous amount of work. The amount of R&D that we dedicate into one singular computing stack is like no other computing stack in the world today. But the benefit is really quite extraordinary. The markets, the first one. The first market we started to cultivate, and this was the, if you will, the tip of the spear of GPU computing. We went to the people who needed more performance the most. In fact, when I came to Taiwan once, one of the most important things, one of the most inspiring things that anybody ever said to me was a quantum chemist, and his son lives in California, and told him about this brand new architecture we created called CUDA. And his father was trying to do quantum chemistry on a supercomputer, massive IBM Blue Gene machine. But it was not going fast enough. And so he went down to basically the retail store, the gaming store, and bought a whole bunch of GeForces, and he came back, he programmed CUDA and on his quantum chemistry code. And he was so amazed by the speed up that he thought the answer was wrong. And he had to wait for many more days for his IBM supercomputer to finish its job, to compare the answer, to realize that it was in fact right. We created for him a time machine. We created the world's first time machine. And he said to me, he said, Jensen, because of your work, I can now do my life's work in my lifetime. It almost brought me to tears. It was just the most amazing thing anybody's ever said to me. And it's just super, super inspiring. And so if you take a look at this industry, this is the tip of the spear. This is where we started. A $10 billion industry. I believe every single supercomputer in the future will be accelerated. It is impossible to build a next generation exaflops machine in any kind of a reasonable budget, in any kind of a reasonable power, using traditional methods. You have to have acceleration. The future of supercomputing is accelerated. And we have now the entire stack. All of the world's top supercomputing codes have now been accelerated with CUDA. We have 550 high-performance computing applications now ported on top of CUDA and accelerated. NVIDIA's GPU is now in thousands of high-performance computing data centers, and some of the world's most advanced and largest supercomputers, including recently announced here in Taiwan, most will build a supercomputer here in Taiwan for researchers, for high-performance computing, and AI. Thank you. If I talk loud and fast enough, the frog in my mouth will come out. The stack, GPU computing, basically works in several ways. The first step, of course, is to build an amazing GPU. That's the first step. The first step is building an amazing GPU. The second step is to create the libraries for that domain. The system software, the systems architecture, the APIs, and the libraries, accelerated libraries for that domain. And in the case of high-performance computing, it's linear algebra, it's FFTs, it's all kinds of different types of libraries, and we have all of the libraries created. And now with deep learning, cuDNN, and with inference, TensorRT, the libraries are in place. The third step is to work with all of the application developers, the solvers, technical teams, work hand in hand to accelerate, to refactor their algorithms of their application and run it on our libraries. If you're able to achieve that, you can achieve 100 times speed up over 5 years, just as I showed before. And then lastly, technical teams all around the world work with the end markets to adopt the technology. So architecture, full stack, application optimization, ecosystem, technical teams working with the market, 1, 2, 3, and 4. This basic methodology has been applied in our company for over 10 years. And so the first application space of GPU computing, a $10 billion supercomputing market, annual supercomputing market, I believe will be completely accelerated in the near future. The amount of computing that's needed in the world is growing, not slowing. Although CPU performance has slowed, demand in the marketplace is in fact growing. This just came out. This is from OpenAI. OpenAI measured what is the amount of computation that's necessary to train the most extensive neural network that year, and he plotted it. This is Ilya, it's OpenAI. He plotted it over 5 years. 5 years. Moore's law in 5 years is 10x. Moore's law in 5 years is 10x. This is 5 years. Starting with AlexNet, in literally 5 years' time, the computation required, the amount of computation that's required to train the network just one time, increased 300,000 folds. 300,000. This is the groundbreaking neural network that started everything, called AlexNet. 300,000 times in just 5 years. The amount of computation that's essential to the future of computing is really quite extraordinary. This is the reason why. The reason is, before this time, software was written by humans. And software engineers can only write so much software. But machines can write enormous software. Machine that doesn't get tired. And it types very fast. With GPUs, it can type very fast. So long as there's data, so long as there's knowledge in how to create the architecture, creativity, we can create absolutely enormous software. And this is the future of computing. Gigantic software. Every single company in the world who develops software will need a supercomputer. NVIDIA today has 1,000 petaflops in operation for our software engineers. And we need a lot more. We absolutely need a lot more. We're building it as fast as we can. For the very first time in our company, over the last 5 years, we had to go build supercomputers so that our supercomputers could write software. Every single company in the world who believes software is their future will have to use AI, and anybody who develops AI will have to have supercomputers to write the AI. Makes a lot of sense. This is one of the reasons why software is going to get larger, it's going to get more complex, it's going to turbocharge into a double exponential, it'll move faster than before, and all software companies, or all companies who develop software, will need AI supercomputers. It is for this reason that we reinvented the GPU. Our GPU has been advancing with more and more performance and more computer graphics capability and more general purpose over time. Every single generation, we made our GPUs more general purpose so that the number of applications we can process, we can accelerate, can continue to grow. However, with Volta, we fundamentally re-engineered, reinvented, reimagined what a GPU is. We created a brand new breed of GPUs, a brand new species of GPU. We call it a Tensor Core GPU. A Tensor Core GPU computes in two fundamental ways, and it's fused in one architecture. The traditional way of computing is to understand cause of a physical phenomenon and the effect. From the effect, learn the cause. From the effect, figure out the cause, the scientific method. And from that scientific discovery, you have a simple way of predicting or simulating the outcome based on the inputs, transfer function of a well-known equation, maybe it's Maxwell's law, maybe it's Newton's law, maybe it's Schrodinger's equations, all based on first principles, laws of physics. Through the scientific methods, we discovered what was the cause, what's the effect. Simple set of equations. Through very large supercomputers, we can predict the outcome from the input. Whether it's fluid dynamics methods or finite element methods, all of them are based on fundamental first principles of physics. There's a new approach today where there are problems we simply cannot, or we simply do not yet know what is the cause. We only know the effect, and we have a lot of data for it. Maybe it has something to do with the restaurants you like to eat. Maybe it has something to do with the books you would recommend somebody to read. Maybe it has something to do with the music that is the most popular. Large social effects have no fundamental root cause. Very difficult to write a simple equation. And machine learning methods where you discover the features and the important structure from data. Through an enormous amount of data, you will discover a way to predict the outcome, deep learning. These two forms of computing will not only solve different problems in the future, they will come together to solve similar problems. New problems will be solved by unifying these computation approaches. The unification of this computing approach needs a new type of processor, and so we invented Volta, the world's first tensor core GPU. It is a multi-precision, multi-architecture approach, and it has the ability to process using traditional scientific methods, FP64, FP32, as well as new inferred methods of computing, probabilistic methods of computing, where the precision is a combination of FP32, FP16, and one of its most primitive operations is a 4x4 linear algebra methods, 4x4 matrix multiply and accumulate. And we can do that at incredible rates. Volta is the world's first processor that unifies all of these methods into one architecture, and we call it a tensor core GPU, fusing HPC, the traditional scientific methods, and the new methods of deep learning, machine learning, probabilistic methods for inference, for categorization, classification, grouping, regressions, predicting the outcome of the future in a world that is too complex and not based on first principle laws of physics. Okay? And so these two approaches have been fused together into our new GPU called Volta Tensor Core GPU. But the world wants even bigger ones. In fact, Volta pushed every limits of physics. It is as large of a chip as anybody on the planet can manufacture. I still remember the first day we started talking to TSMC about Volta. The yield would have been 0 chips per wafer. And because of all the high-speed memories, and because it's 3D stacked, the yield of a module would be exactly 0. And because we have to connect all of them together and operate them for hours and hours and hours because it's a high-performance computing problem, the fit rate is instant. Fit rate, failure in time, meaning it never works. When you combine all of these factors together, Volta was an impossible machine. And that's why we thought it would be perfect to work on it. And so all of our teams dedicated ourselves for several years, and we created the world's most advanced GPU, the most advanced processor. We call it Tensor Core GPU. And then, as soon as we launched it, everybody told us, can we have it bigger? And so we said, why don't we make it even bigger? And so we challenged ourselves to create a new programming architecture, a new switching architecture, and we made it possible to connect 16 Volta Tensor Core GPUs together all at once. Here's the challenge. Many researchers would like to do model parallelism. There's model parallelism and data parallelism. Model parallelism is to take a very, very, very large model and break it up into small pieces and to have a whole lot of processors working together to simulate that model. Which means that every single processor has to coordinate with every single other processor. There's the other type of processing, which we do very, very well, but it's data parallelism. One model that fits into one GPU, 16 GPUs or 1,000 GPUs, all running different data, but on one model. One GPU, one model, as many different types of data as you like. Data parallelism. Model parallelism, there's no shortcuts. You simply have to create an architecture that when all the processors are synchronizing with each other, it continues to scale. And so we created a new type of computer with a new type of switch. And this new switch, called NVSwitch, has the ability to transmit the programming protocol, the memory protocols, and the semantics of memory all the way through the bus so that everybody, all of the other GPUs look like one GPU, and everybody's memory looks like your memory. Connecting all of this together, unfortunately, requires an enormous amount of bandwidth because these GPUs are so fast. They get work done so fast, they're constantly communicating. So the communication overhead is very, very high. Well, we went off to try to solve that problem. We created a brand new system called an NVSwitch. And together, as a result, our GPU, this virtual GPU, the virtual gigantic GPU, has 512 gigabytes of memory. It's like a frame buffer today for a gaming card is like 2 or 3 or 4 gigabytes. 512 gigabytes of memory, high-speed memory, all working together. 80,000 processor cores in this one virtual GPU, and has 2 petaflops of computing, all pretending like, looking like one GPU. It's made out of a switch, a brand new type of switch. We call it the NVSwitch. It's 2 billion transistors, has 18 links, basically 3 NVLink ports. It can connect up to basically 2 GPUs and another switch or 3 GPUs. We use 6 of them on top and 6 of them on the bottom to connect all of 8, which basically says every one of the GPUs can talk to every one of the GPUs simultaneously. Every one of the GPUs can talk to every one of the GPUs simultaneously at a bandwidth of 300 gigabytes per second, 10 times PCI Express. Okay? It's basically like every single GPU has 16 PCI Expresses that are 10 times its bandwidth connected to each other, so that everybody can talk to each other all at the same time. It's built out of 12 nanometer TSMC's process, 2 billion transistors, the fastest SerDes that I know. Altogether, each chip has 900 gigabytes per second of what is called cross-sectional bandwidth. The aggregate bandwidth that crosses that chip at one time, 900 gigabytes per second, and multiply that across all 16. Basically what happens is, let's do some simple math. 900 gigabytes per second. A movie is like 50 gigabytes per second. So we could move essentially across the backplane 300 4K movies in 1 second. 300 movies. None of us can name 300 movies. We could put 300 movies on this backplane and it will be transferred to each other like that. Okay? Kind of crazy. But by doing so, we've now created one virtual GPU. And a programmer can program this one gigantic virtual GPU. Let me show you what it looks like. It looks like this. This is the world's largest GPU. It can even play a game. The world's largest GPU. 30 terabytes. I already told you, 50 gigabytes is one movie. So 4 times 30. Okay? So 30 terabytes, so 4 times, 120 movies, 4K movies could fit into the non-volatile storage. PCI switch to connect the GPUs to the CPUs. 1.5 terabytes of system memory. A regular PC is about 32 gigabytes. So it's a few hundred PCs of memory, system memory. 2 of the highest performance Xeon Platinums. And each one of the trays are 8 GPUs, and it's connected through this backplane that connects the top tray and the bottom tray, all NVSwitch protocol, all running at 300 gigabytes per second per GPU for every connection. As a result, you have two petaflops, 512 gigabytes of HBM2, 10,000 watts. 10,000 watts. This is what the world's largest GPU looks like. £350 pounds. Ladies and gentlemen, two of me. So this, I was going to say this weighs as much as two of me, but I think I'm being too generous to myself. 350 pounds, 10,000 watts, 2 petaflops, one operating system. One operating system. This is the fastest single-node computer humanity has ever created. One operating system, one programming model. Program this as one computer. This is like a PC, except it's incredibly fast. Okay? What you're looking at, this is also fun. You know what our NVIDIA's creative department did? Do you guys know stop motion animation? You moved something a little bit, you take a picture, you move it again a little bit, you take another picture. Stop motion animation. It's like back in the good old days, claymation. Okay? And so our creative department, instead of rendering it, it's so beautiful. We blew it up. Stop motion animation. You want to see it again? It's so great. Here, watch. Only NVIDIA people get so excited about this, right? We have a fun job. But you know what's amazing is when you look at this entire stack, look what happened, okay? We took a new GPU called Volta. We added 32 gigabytes to it, so now it's the largest graphics chip in the world. And then we created this thing called NVSwitch. We connected 16 of them together into one virtual GPU. We had to create a whole system architecture, brand new operating system, and create the entire stack of software on top of it. But what's the benefit? The benefit is amazing. The benefit is this. Look at this. Literally 6 months ago, NVIDIA announced DGX-1. Or 1 year ago, we announced DGX-1. 6 months ago, we upgraded with 32 gigabyte Volta. And this is all of our software. 6 months later, we created this whole new computer. The entire stack has been updated. Everything has been updated, everything enhanced, new technology invented. As a result, we improved the training speed of deep learning by a factor of 10 in literally 6 months. There's a new law in town. You guys didn't understand that joke? There's a new law in town. This new law of computing says if you are able and if you are willing to optimize across the entire stack, the performance optimization, the performance improvement you can achieve is incredibly fast. But you have to know how to operate across the entire stack, one stack at a time. And so 10x in just 6 months. Does that make sense? Well, Ilya at OpenAI, he's the head of OpenAI. Ilya at OpenAI needed 300,000 in 5 years. 300,000 in 5 years. Okay? So this, if it's 10 in 6 months, 5 years is 10 periods, right? 10 to the 10th. If we can keep going like this, computing is going to see no boundaries. There is no end to the future of computing. You just can't do it the same way anymore. You have to do it the GPU accelerated method. 10x in 6 months. DGX-2 is $399,000. $399,000. $399,000. This is the highest price graphics card NVIDIA has ever made. $399,000 is available in Q3. But the value is incredible, you guys. 好便宜啊. Did I say that right? 对了哈，拍谁随便讲哎。$399,000. What an incredible value. Let's take a look. All right, so if you had to compare this computer, all right, this sexy computer right here, you could take this computer to bed. It will fit nicely. I love this computer so much. I will have one, okay? $399,000. Look at this. It would take this many computers, 300 dual CPU servers, $3 million. $3 million. 108,000 watts. Are you ready for this? Oink. Here, take another look. Look at that. Before, after. Oh, so sweet. And you save so much money. You save $2.5 million. In fact, you will save more money on the cables in the back of that computer than to buy this computer. So beautiful. 那么漂亮. Wow. 漂亮也便宜. So good. Ladies and gentlemen, the world's largest GPU, the DGX2, incredible value, $399,000, and it will be able to run models and do model parallelism like nobody has ever seen before. Now, let's compare against Ilya's chart of 300,000 times, shall we? So, in a few years ago, just 6 years ago, Alex Krizhevsky at the University of Toronto, working for Jeff Hinton as his advisor, created this brand new network called AlexNet. And he trained it on 2 NVIDIA GPUs, 2 of our high-end NVIDIA GPUs. And it took him 6 days. He submitted his result and won the world's leading computer vision contest. Without understanding computer vision, he became the world's leading computer vision researcher. But by inventing a new way of writing software called deep learning. Time to train AlexNet was 6 days 6 years ago. It is now 18 minutes. 18 minutes, 500,000 times. In fact, the reason why deep learning has advanced 300,000 times is because NVIDIA's GPU accelerated computing platform has advanced approximately the same time. They used every drop of power performance that we delivered every step of the way. And every neural network breakthrough still takes about 6 days. So today, you would get a DGX2 and you would run an amazing neural network model to discover the next future software, and it will still take you 6 days. That's why it's so vital for all of us to continue to push the limits. Well, pushing the limits, and driving everything to the speed of light has enabled us to make great contributions to deep learning. And today, if you look at our platform, today I want to announce something. It's really quite something. We're announcing today that we have achieved 5 speed records. The fastest single chip for training, this is training ResNet 50, much more complex than AlexNet, Okay, this is today's modern state-of-the-art computer vision network. ResNet 150, single chip record, single node record on DGX2, 15,000 images per second for training. The fastest training time at scale, give you all the computers in the world, how fast would it take you to train ResNet 50? 14 minutes. Once you're done developing the network, you have to run it in operation. Just like you write the software in C++, but you have a .exe, the runtime. The runtime is right here. This is the runtime of deep learning. It's called inferencing. Okay? The runtime of deep learning, the latency is really important because when you're doing speech synthesis or when you're talking to hello and you're talking to a neural network, and that neural network has to respond pretty fast. The latency of a neural network is really important. This is a speed record, 1.1 millisecond. People have always said that NVIDIA GPUs have very high throughput, but the latency was a problem. That's just because they don't understand our GPU. Our Tensor Core GPU, 1 millisecond. No CPU could touch it. No FPGA could touch it. No ASIC could touch it. 1.1 millisecond. And then this, at the hyperscale data center level, because you have millions of people who are querying the internet and querying the data center and running their application, each one of those applications will touch many neural networks in the future. So the throughput of the data center will directly affect the number of customers you can support, the quality of service you can provide them, and, very importantly, the cost of the data center. And so the throughput is incredible. Just to put this in perspective, a CPU is 4. Not 1,000, not 100, just 4 images per second. We now have achieved 6,000 images per second. And as a result of all of this, the more you buy, the more you save. That's right. Because in the future, as you know, in the past, when a microprocessor performance goes up, Moore's law is about decreasing the cost of computing. Moore's law is about decreasing the cost of computing. When performance goes up, cost comes down. They are cousins. In the future, the new law is data center performance. And if the data center performance goes up, the cost comes down. And we are going to drive performance in the data center up like nobody has ever seen before. And the reason for that is because, obviously, we could drive costs down, save money for everybody, but more importantly, because I believe that the number of applications and the type of software that machines will write in the future will be gigantic, and we need the performance. So 5 speed records. The type of neural networks that are being developed all over the world is just amazing. And so we thought we would show you one example. NVIDIA has one of the great deep learning research teams. And Quailin has been so gracious to come to Taiwan for the very first time. And he's been doing research in a type of neural network that's really, really clever. And so this form of neural network not only recognizes your speech, but it can predict, it could synthesize, it could generate images almost at superhuman levels. Okay? So, Quailin, let's take a look at that. Okay, so here we're going to show you left and right. Let me set it up, and then you can show us, okay? Left and right. These 2 pictures are the same. Quailin is going to modify the one on this side. So he's going to modify the one on this side, and you will see the result on this side, okay? Now, of course, he's going to modify it over here, and you could decide whether the modification is almost superhuman or not. All right, go ahead.
Okay. So let's try to remove the cable here.
It's okay. Oh, that cable is so ugly. Let's get rid of that.
Okay. Also try to remove the.
Oh, come
borders,
on.
okay.
Really? We need to keep some because we need people to know this is Taiwan.
Okay. Let's also try to remove the yellow taxi.
Automatically, it figured out what it should look like. And it drew based on what we would have drawn. Okay? Pretty amazing, superhuman levels. Let's get rid of this car. This car is running a red light. Let's
Okay.
protect that guy. Oh, come on. See, I gave you a trick one because that car had a light, right?
Okay. Yeah.
I gave you a trick one. Ah.
Let's try to remove the.
Really?
The lamp.
Come on. No way. No way you could do that. See, I could trick scientists. Ladies and gentlemen, before, after. So good, right? Incredible. Let's do another one. Let's see if we could find the limits of your artificial intelligence network.
下个什么 Okay.
再来一个。
Let's show the before and after.
That's so good. Okay. Let's do another one.
Next one. So.
Oh, yeah, come on. This is so beautiful. Get rid of this thing. Get rid of this bin. Why is that building there? Doesn't make sense. Oh, so beautiful. Get rid of this thing. Add more forest. I want more forest. Can you give me more forest? I want more forest. Wow. That's incredible. Let's do another one. That's beautiful. Before and after. Look at that. This is 2017, and this is 1800. Okay, let's do another one. Kraylin, let's go to another one. Oh, I love this one. I love this hotel. But that light pole is terrible. Let's get rid of it. There's no way you could do this one because this light pole is in front of a tree and in front of a hotel. How could you do it?
Okay, let's see if we can get rid of the pole.
Wow, that's amazing. And so this neural network has learned how to generate images. It looks at all of the surrounding pixels and it says, what would be the right images to replace it with? Okay? It's essentially what we would do. We would imagine what's the surrounding pixels and what's the image, and we would try to predict how to replace it. Wow. This is Taiwan before cars, before electricity. What do you guys think? How 聪明啊! Artificial intelligence. Let's do another one. Let's do the last one. Let's do one more.
Okay.
Let's do one more. That's not me. I'm younger. Okay, let's make Ang Lee look a little younger.
Okay.
Yeah. And Make him lose a little weight. I've seen Ang Lee lighter before.吃太多点心了。Oh. Ang Lee was very attractive, huh? He's very attractive. Look at that. Oh, that's perfect. Wow. Okay, go set translucent on so we could see before and after. We took 10 years off his life. Look at that. Look at that. That's incredible. Okay, Kraylin, I want you to go through all the internet photographs of me and fix it, okay?
Okay.
All right, good job, you guys. Ladies and gentlemen. People are doing amazing work in artificial intelligence all over the world. Here in Taiwan, we're seeing some really great work done as well. Foxconn is training a neural network to do visual inspection, looking for manufacturing defects. And you know how many things that they manufacture and at what speed they're manufacturing it. And so the ability to be able to detect the slightest anomalies in using visual inspection, using an artificial intelligence network will help them improve their productivity, improve their throughput, and reduce cost. Healthcare. Doctors at the CMU, the China Medical University Hospital, is developing a neural network to detect cancer metastasis. At the National Taiwan University, they're developing a neural network to segment organs, looking for potentially organs at risk. Okay, public safety. AI Labs is working with the Tainan city government. Apparently, there's just a whole lot of bridges, 1,600 bridges. I had no idea. 1,600 bridges in Tainan, and they, because of the typhoon, there could be potential structural damage. They teach drone how to fly around and look for structural damage. The Taoyuan city government is working on autonomous vehicles. They would like every closed path vehicle, constant path vehicle, to be autonomous in the future. Makes perfect sense. Okay, so everybody, as you can see, whether it's in healthcare, in manufacturing, in smart city, you're seeing all kinds of really great work being done in AI. It all started 6 years ago with the AlexNet. Alex Krizhevsky, as I mentioned before. It was only 8 layers deep, and about 1 million parameters, 1 million numbers. This body of computational graph was 8 layers deep, about 1 million parameters. In just that short time, and this one network ignited the revolution of modern AI. It was able to solve a problem that is essential for artificial intelligence, for software to interact with the real world, by discovering the important features of a large amount of unstructured data automatically. The front layers, the convolutional neural network layers, was able to discover the essential patterns that would classify an object, and it did it automatically. You don't have to write any software. You just have to give it a lot of data, and it needs a lot of supercomputer, to be able to discover the interesting patterns out of information by itself. It's like you and I being able to discover patterns out of experience. We live in experience, we do something, and over time we say, hey, this pattern exists, and it keeps emerging. And then we generalize that pattern into knowledge, otherwise known as intelligence. The ability to recognize features, recognize important patterns, create the structure of the data, of the patterns, and generalize it hierarchically into knowledge, revolutionize modern AI. From there, it just took off. Look at that. People thought that CNN was the beginning and the end. It was just barely the beginning. Since then, Cambrian explosion. Just literally every single type of neural network has happened. CNNs, not only has it gotten more complex, different layers are all created. RNNs to recognize sequential patterns. CNNs recognize spatial patterns. RNNs recognize sequential patterns. The combination of the two does amazing things as well. You also have generative adversarial networks. A neural network, that's essentially two networks. One network trying to generate an image. Let's use image as an example. One of them generate an image, generate a sound, or generate a story. Okay? One of them is generating. The other one is testing the output of the generation to see, is it good? Is it real? Is it good enough? And the two of them are competing with each other. That's why they call it adversarial. It's a generation network, but it's adversarial. And as a result, when both of the networks become super good at generating new ideas, the other one testing to see if it's good or real, the GAN generates outputs that are basically superhuman. And so generative adversarial networks, reinforcement learning is like the way we learn. Trial and error, try this, try that. When we're learning how to walk, we use reinforcement learning. We try it, and if we do a good job, we get a reward. If we do a bad job, you get a disincentive. And so you try it over and over and over again. This is how we're going to teach robots how to be good robots. And then there's all kinds of new species that are still coming out. In just 6 years' time, thousands of neural networks have been invented, and the complexity of it is incredible. A lot of people ask me this. The GPU is fantastic at training. The performance that you have is incredible at training. But what about inference? What about inference? In fact, we know this. The inference problem is even harder than the training problem. And the reason for that is because in a large-scale data center, now for a little tiny device, for an appliance like a Siri or a smart speaker, smart microphone, it's very trivial. But for a large-scale data center, for a high-performance data center, the type of networks that you're running inside this data center is very diverse. And they're all very complicated, and they're growing constantly, and they're getting more complicated over time. I created a simple way for you to think about inference. Inference is like plaster. Okay, are you guys ready? Plaster. The P stands for programmability. In order for the data center to be able to support all kinds of neural networks that are being created by all of the engineers inside and outside your company, that data center cannot only run CNNs. That data center has to be programmable. So the first thing, you need programmability. The second thing is you need a processor that has very, very low latency. As I mentioned earlier, the speed record of latency, 1.1 milliseconds, the latency directly translates to if you say, okay, Google, you want it to come back instantaneously. When you say, okay, Siri, you want it to come back instantaneously. You want the result. You want the inference to happen with very low latency. Third, accuracy. You could sit here and return answers as fast as you like, but if the answers are wrong, it's very frustrating. So the accuracy of the network is very high. You trained it with 32-bit floating point. The question is, when you run it in the data center, what kind of precision are you willing to enjoy? The accuracy has to be programmable. Third is size. The smaller the network, the more you can put inside the data center. The size of the network has everything to do with the speed and also the power of the data center. T for throughput. Ultimately, you have millions and millions of people. They're sending queries of all kinds. They're taking pictures. They're asking questions. They're talking to their computers. And now in the future, you're going to have all kinds of smart microphones. Everybody's going to be talking to everything. They're all going to be connected to this hyperscale data center. And so the throughput of the data center is directly related to the cost of the data center. Energy efficiency. A third of the total cost of operations is energy. And then lastly, rate of relearning. The rate of learning. The thing that we know about software is that software needs to be fixed. There are always bugs. There's always something that it didn't recognize properly or something that it's not doing properly. And so once you deploy the neural network into operation, as quickly as possible, you're probably going to have to fix it. And so the rate of learning and redeployment into the data center is really important. If you have to change the design of the ASIC every single time, imagine your rate of learning. imagine your rate of fixing bugs. And so plaster, programmability, latency, accuracy, size, throughput, energy efficiency, rate of learning. There will be a quiz at the end of the keynote. Okay? The first quiz is if I say, the more you buy, the more you save. That's the right answer. The second is plaster. What does the P stand for? Programmability. Very good. All right, good students. All the world's best students right here in Taiwan. In order to serve this market, in order to allow all of these complex neural networks to now go into the data center, we have to solve several things. The first thing, of course, is that the type of neural networks is really quite diverse. You got speech synthesis, speech recognition, speech synthesis. You have natural language understanding. What did you mean? You have natural language translation, translating from one language to another. The universal translator in the future, you'll talk to it in Chinese, it'll come out the other side in English. So when you're making a telephone call, you could talk to anybody in any language. Okay? So natural language understanding, language translation. When you make a recommendation, when you buy something and make a recommendation for you, what kind of news would you want to read? What kind of movies would you like to watch? Those kind of recommendation systems, recommenders. Okay? And of course, speech synthesis, recommendation, natural language, okay, image, video. Okay? And it could be video, could be captioning the video. It could be detecting inappropriate video. And so all of these type of content is coming into the data center, and we want to be able to run all of these different types of neural networks models. Well, these models, the output of a training neural network framework is a gigantic file. It's a gigantic file. It's not a source code, it's a computational graph. Okay? This computational graph has weights and biases and gradients. After you're done training, it has a whole bunch of weights. And so all these different weights, they're connected to different nodes, and they're massive. They're all kinds of different types of layers. What we need to do is we need to take the output of that training, and make it run plaster. It has to be low latency. We have to improve the performance. We have to reduce the accuracy wherever we can, but protect the accuracy wherever we must. Get rid of unnecessary nodes. Compress, fuse, remove layers. And so the optimizing compiler is studying the graph and creating a new graph. The output of the graph of a framework and the graph that we run are fundamentally different, but has the same result. And so that compiler is called TensorRT, a new type of optimizing compiler. Whereas we used to have C++ compilers, we now have neural network compilers. Okay? And so this neural network compiler is called TensorRT. It's a big piece of software that is very, very difficult to write. A lot of groundbreaking work that we're doing here. We're supporting more and more types of networks and graphs. We're supporting more and more type of NVIDIA GPUs, from the traditional CUDA to INT8, 8-bit integer, to Tensor Core. And we're supporting more and more compiler techniques. At GTC, we're announcing that this generation, we have 4 new features. TensorRT 4.0 has now been integrated. Google has integrated TensorRT 4.0 into TensorFlow so that it is a native output compiled. TensorFlow, Kaldi, which is the world's most popular natural language framework, Kaldi has been optimized for TRT as well. And Onyx, which is the export format of PyTorch and MXNet, is now accelerated by TensorRT, and WinML, which is Microsoft's format, also accelerated by TensorRT. The result of it is pretty amazing. Whether it's image or video, 190 times, natural language understanding 50 times, recommendation systems 45 times, speech synthesis 36 times, speech recognition 60 times. Basically, what's happening here is by recompiling the software that you're running in your data center, the neural networks that you're running in your data center, and you add a Tensor Core GPU into your data center, you could save just an enormous amount of money. Let me show it to you. But before you could run it in the data center, you have to do something else. The hyperscale data center's infrastructure software is very complicated. There's a piece of software called Kubernetes, which takes all of these different accelerated stacks and it containerizes it. We containerize it. And NVIDIA's GPU is the only accelerated processor that has a Docker container associated with it. The only accelerated Docker. So NVIDIA GPU containers, which is accelerated with Docker, can now be deployed as a container. You run the container on top of Kubernetes, and you could scale it out into all of the resources within the data center, in fact, even outside of the data center. And as more workload happens, more servers are spooled up. As the workload disappears, the servers are released. And if anything were to happen to a server, it moves the job somewhere else. So Kubernetes is the hyperscale, if you will, operating system. Kubernetes is now GPU accelerated. So if you look at this entire stack, from the GPU to all of the APIs and libraries that we created, that you can now accelerate applications to put into a Docker, into a container, which then runs on top of Kubernetes. That entire software stack is so complicated. It has been the work of hundreds of our engineers for several years. Let me show it to you. Okay, this is a CPU doing image recognition with ResNet 152. This is 152, right?
Yep.
Okay, this is ResNet 152, the most advanced image recognition network out there today. The Skylake CPU can do 4.5 images per second. Not bad. Pretty amazing. It could recognize flowers of all these different types. Let's stop at one. Right? These flowers, incredible. Garden phlox. I bet no one has ever said the word phlox before. If you told me what's a garden phlox, I have no idea. Snapdragon is not that. Snapdragon's a chip. Thorn apple. Thorn apple is an apple, not a flower. Lenten rose. So none of us would have passed this test. This neural network can detect flowers at superhuman levels. None of us would have been able to pass this test. Impossible. But yet a neural network running on a CPU can do that. Millions and billions of people could take pictures or do whatever they want and look for a particular object they want to buy, send it up to the cloud, and the cloud will say, that is a brand new leather jacket. Okay? And it will tell you where to buy it. And so imagine all of the people that are using neural networks in the cloud. And so last year, we were here, and I showed you the state of the art in inference performance. And it was 580 images per second. This is 4. And so when I showed you 580 images per second, the audience went, wow. Okay? That was 1 year ago. But as you know, we have many engineers, and they've been working very hard. At GTC a few months ago, right?
Huh?
Are you still with me?
Yep.
This is GTC, 1 GPU. Last year was 580. At GTC a few months ago, 970 on one Tensor Core GPU. One GPU. One GPU is now 250 times faster. How could you add something to the most advanced CPU in the world and run 250 times faster? If you think about that for just a second. And as a result, the amount of throughput you can enjoy in your data center. But see, that's not enough. We have so much more architectural mojo, magic, that we are going to show you our latest results. Ladies and gentlemen, the brand new TensorRT running on our Volta Tensor Core GPU. (2,500 inferences per second. Now, if we make this go any faster, NVIDIA 不会赚钱了，大家买一块就好了。But thank goodness, the world's internet is consuming so much machine learning capability. And our job is to simply drive the cost down as fast as we can and improve the performance as fast as we can. And so all of the software and the layers and layers and layers of software that goes on top of our GPUs make this possible. So this is TensorRT4 on Tensor Core GPU, but that's not enough. We can do more. And so we ported Kubernetes accelerated with our GPU. We call Kubernetes on NVIDIA GPUs. K-O-N-G. Kubernetes on NVIDIA GPU. Okay? You cannot K-O-N-G. Kong. Yeah, Kong. And so Kong, let's show them Kong.
Sure. So imagine you need more performance. So let's step back and see what happens.
Thank you.
So in this case, our load has increased. So now we need more compute. We need to bring in more processors to do computing. So let's add those in. There we go. So we brought 4 new V100s online. And
so just now, all of a sudden, all of your customers showed up, and you're so happy, right? But if the customers show up and you're so happy, you cannot send IT manager to the data center and add more GPU. This will naturally scale by itself. Kubernetes will simply scale it up. Okay, so 4 GPUs now. Each GPU. Wow. Wow. Look at that. That's all customers. You can have 4 customers, or you can have 10,000 customers. This is much better, right? 这样子赚钱比较快. Okay?
And Kubernetes doesn't just scale for your on-prem data center. You can also burst out into the cloud. So if you need to add more capacity, I'm going to add 4 nodes from AWS. You'll see them pop in. And we can add those into the load balancer. And we're going to see another doubling of performance.
Pretty amazing. Now, the amazing thing is this. Look at this. 1 GPU is in Amazon, and the 4 GPUs are in Amazon. These 4 GPUs are in a DGX computer in Santa Clara. And now we can run all of this workload completely invisibly and scale it up, all running Kubernetes GPUs. Okay, thanks a lot, Ryan. Good job. Okay, so I talked about high-performance computing. $10 billion market. We have a specialized acceleration stack for all of the high-performance computing and supercomputing applications. Molecular dynamics, whether simulations, particle physics, fluid dynamics, physics simulators, quantum chemistry, you name it. Okay? And we also have all of our AI for deep learning, which is training all the different frameworks. We support every single framework in the world. Now, we have an accelerated stack for hyperscale inference. For hyperscale inference. You take the same GPU, you can now run it into the entire data center. The world's data center in the cloud is about 30 million servers today. I believe every single node will be accelerated in the future. Every single node will be accelerated. And the reason for that is the value proposition is too compelling. From 4 images per second to 2,500 images per second. The throughput benefit is so great. Adding a GPU, we simply need compiler, so complicated, TensorRT 4.0, running on top of CUDA, running with cuDNN. We have all the necessary infrastructure, software, developed on top of that, container software, Docker, running on Kubernetes, accelerated by GPUs. This entire stack is fully accelerated. The number of customers that are jumping on this platform is really quite exciting. We have customers in the United States and China. We have internet companies. We have people who are doing smart city. We have people who are designing cars. Applications of all kinds. Okay? So the third market. AI for training, AI for inference, high-performance computing. Today we're announcing we're announcing something new. These servers are really hard to design. They're supercomputers. They're hard to design. And they're hard to deploy. The architecture is complicated. It's very high performance. The amount of power density is very high. Notice we took several 100,000 watts and reduced it down into 1 or 2 racks. So the power density is increased. The compute density is increased. And so the server designs are complicated. We've been working with all of the leading server companies in the world. They happen to be all right here in Taiwan. And so today we're announcing a brand new architecture for future hyperscale data centers. We call it the NVIDIA HGX2. Let me show it to you. Oi! All right, this is the HGX2. Can you guys see this? This is 350 pounds. I'm very strong. Look at how many TSMC transistors. Anybody from TSMC here? 100+ billion transistors, all right here. 8 GPUs connected by 6 NV switches. The NV switches connect each one of them, one to each other, and then all of them to all of the others. Okay? So 300 gigabytes per second of communications between every single GPU. Every GPU is about 300 watts, 300 times 8. And the NV switch protocol comes in through the back. And so this is basically, as you know, the ATX motherboard revolutionized the PC industry. And just as Taiwan was at the center of the PC revolution and at the center of the cloud computing revolution, we are gearing up together to start the AI revolution. And the type of computer is different for each type. Every computing revolution required new computers. So you remember the power of the PC AT and the ATX motherboard. The standardization of that motherboard accelerated the velocity of computing tremendously. This is a hyperscale data center motherboard standard. And we will ship literally together an entire motherboard just like this. And this is incredibly heavy. Oh, here we go, Paul. Yeah, be careful. That is $200,000. And they're connected in the back by this high-speed backplane, which connects all of the NV links directly into this, and 2 motherboards, and then you clamp it in. Supercomputer with just 3 motions. 1, 2, 3. Okay. The future of computing made easy. 哇，我要坐下子。You have to be a good athlete to be a CEO. Wow. Okay, all right, so we are at the epicenter of the future of the AI revolution. And our partners, I'm so grateful for our partners. In the last 10 years, this country produced 100 million servers. 100 million servers for data centers and cloud, representing 90% of all of the servers produced in the world. It's produced right here in Taiwan. The world's leaders have all adopted the NVIDIA GPU acceleration architecture. From Quanta, the Foxconn, WeWin, Taiwan, Inventec, ASRock, Acer, Gigabyte, ASUS. With your partnership, anybody who wants to use this future way of fused computing with HPC, high-performance computing, and AI can. Doesn't matter where they are. It doesn't matter what industry they're in. Doesn't matter what markets they serve, what data centers they run their operations from. We have servers of every single kind. I want to thank you for your partnership, all the engineers that work with us on making this revolution possible. Thank you. We now have, with the HGX2, a growing family of servers. Look at all the different configurations. We have HGX T1 for 8 GPUs, 2 CPUs training. The new HGX T2 for training and for supercomputing. HGX I1 for inference. HGX I2 for inference. So depending whether you want one use things, low powers, or you could aggregate more computing into a node. You have the SCX E1, Otherwise, I call her Sexy 1, Sexy 2, Sexy 3, and Sexy 4. Okay, these are all of our different types of servers. And notice all the different applications that they serve, from different configurations, different power levels, for different rack power density. They could be used for training, inference, high-performance computing, for smart city, for VDI. NVIDIA has a full software stack for Grid. We call it Grid, and Quadro Virtual Workstation that allows you to take all of your PCs and put into the data center, VDI and remote workstation, and for rendering. Just about every way you would like to enjoy the future of high-performance computing is represented here in Taiwan. And so I want to thank all of you for your partnership. It's really fantastic. Thank you. Every server maker is adopting the architecture. Every IT company has. From IBM to Dell to HP to Supermicro and many others. Every single market, whether it's enterprise, the cloud, of all industries, of all countries, are represented. We can now take this computing model to literally anybody and everyone. Okay, so widespread adoption of IT companies. Now, I just described the architecture, the system architecture, the interconnect, but what about the software? Because how are you going to get the software? The software delivery is one of the most complex things because there's so many different layers. The operating system, the containerization, all of the APIs, the libraries, and the accelerated stacks are all so complicated. You saw all of the different version numbers, 5.0, 9.2, so many different versions. How do we possibly deliver the software to the marketplace? There are so many fragmented markets, from life sciences to deep learning, to people who are designing cars, to manufacturing, to smart city. How do we possibly deliver all the software? So we created a new way of software delivery. We call it the NGC Cloud. NGC Cloud is a registry. It's simply a storage of all of our software in container formats. They've all been containerized. Every single layer of the software has been accelerated, has been tuned, has been tested. We can reproduce the results. It's all up in NGC Cloud. 20,000 companies have come to download NGC Cloud because the acceleration software stack, if you can get a really wonderfully tuned version, the performance is so fantastic. Okay, and so the GPU containers now contain all of the deep learning frameworks, a whole bunch of the most popular high-performance computing codes, visualization codes, and we're going to keep on going. There are 30 applications, 30 containers in there today. We've certified it on a number of clouds, AWS, Google's cloud, Ali Cloud, Oracle's cloud, and also for the DGX. And we're in the process of certifying systems of all different kinds. And so anybody who would like their system certified, just contact us and make sure that we prioritize it. GPU containers. So from the architecture to the systems to all the software, we're putting it together. So let's do a bit of a status report. So initially I said I was going to fill out the schematic. Okay, the first part has to do with the accelerating computing stack. A brand new type of processor called the Tensor Core GPU, NVSwitch, a new type of system called DGX2, and the entire stack on top of it. 850,000 developers, 550 applications. Without killer apps, a new computer is useless. And then without the ability to deliver the architecture and the systems to the marketplace, of course, people cannot enjoy it. We have all the leading server companies in the world, all the IT companies in the world, and every single cloud has NVIDIA's architecture inside. This has been the work of 10 years. It has taken us a decade and billions of dollars to get from there to here. Creating a new computing architecture, creating a new computing platform that everybody and anybody in the world can use has not happened since PC, has not happened since AWS, and it's happening again. And so creating a new computing architecture is incredibly difficult, and it's taken us a decade to get here. All of the software will be delivered in our registry. It will run on any cloud. It will run in every cloud, and it will run in every data center. I talked about 2 markets, AI for training, AI for inference, and we started with supercomputing. Now, I want to talk to you about 4 new markets. 4 new markets. The AI market alone is the future of software. There's not one company, not one industry that's not going to be affected by it. High-performance computing is $10 billion. Computer graphics has been the driving force of GPUs since the beginning of our company. Computer graphics is really very unique application. It is both computationally incredible as well as the volume is great. But we, up to now, have not served every single segment of computer graphics. The segment that we have never served is called CGI, computer-generated images, photorealistic images that are used in several applications. This is all rendered on CPUs today. They call them render farms. Games, every single game that looks beautiful is partly rendered in real time, but partly the global illumination, I'll show that to you in just a second, the global illumination tends to be pre-rendered, it's very complicated to do, and it's baked into the textures. Movies, several 100,000 frames per movie, say 300,000 frames per movie. Each frame of the movie takes several hours to render. So just rendering the film from the beginning to the end one time will take, well, hundreds of millions of hours. And that's the reason why supercomputers are created, called render farms, to go render the movies. Every single car advertisement you see today, they're not taking the car and flying into Paris, flying to Shanghai, flying to Taipei. They're not doing that. It's all computer-generated images. And so it has to be photorealistic. The buildings of today are no longer square. A building today is like a product, except it's gigantic. It's not a square box. And so as a result, the only way to understand the feeling of it, the dynamics of it, is to render it photorealistically. Every single one of them are rendered that way. We would like to take that rendering, in fact, and put it into virtual reality so that you can enjoy photorealistic rendering in real time. These things are simply not possible today. Ladies and gentlemen, after 10 years of R&D, literally 10 years of R&D, trying, prototyping quietly in our labs, we're going to announce this year the most important breakthrough in computer graphics, in my opinion, since the beginning of computer graphics. And this is going to be the greatest contribution we've made to this industry in the last 15 years since we invented the real-time programmable shaders that revolutionized modern computer graphics. It's called the NVIDIA RTX. The NVIDIA RTX fuses 3 fundamental methods of generating images. One, the GPU architecture has been revolutionized, as I mentioned before. A brand new type of real-time computer-generated graphics. Second, real-time ray tracing. And third, deep learning, artificial intelligence. By combining these 3 technologies, we've been able to achieve something that we thought wasn't going to happen for another 10 years. We've been able to achieve real-time film quality rendering. Let me show you what that means. This is what GeForce renders. It's beautiful. As you guys know, that if not for the programmable shading technology we invented, modern computer graphics would not look like this. This is through just an enormous amount of R&D that has allowed us to get here. And this is just beautiful. This is modern computer graphics. And yet, when you compare this to photorealistic images, this is what NVIDIA RTX looks like. Can you guys see that? You want to see it one more time? Before, state-of-the-art, real-time GPU technology. Before, after. Let me break it down a little bit for you. So here's one. So ambient occlusion is the surfaces, the intensity that is reflected on the surface of materials from the ambient light. And the ambient light is coming from every direction. Unlike spotlight, which comes from one direction, it's easy to compute, ambient light comes from every single direction. And notice the shadows in the creases. This shadow in the creases comes from ambient lights. It's called global illumination, and that's called ambient occlusion. The part of the scene that has low intensity from the ambient light. And so here you can see this right here is not a shadow, it's ambient occlusion. It's very difficult to do. Let me show you what ray tracing does. Look how beautiful that is. It's like grape juice, Chateau Latour wine. Grape juice, great wine. Pot stickers, Ding Tai Fung. Okay? You see this? Look at this. Look how that looks, right? Look how beautiful that is. Look at it today. Can you see that? Subtle little things, but when I put this in motion, you can all see it. Okay, so that's called ambient occlusion. You need global illumination for that. Reflection and refraction for a translucent material, light from all the different sources passes through the material, and some of it is reflected, some of it is refracted. Okay? And so this is traditional methods. We use a technique called screen space refraction, which is very advanced. And we invented it, but this is a better way of doing it. You see that? RTX, GTX, RTX. And as a result, you get this effect called caustics naturally. When you have light, sunlight over a swimming pool, you see the beams on the bottom, okay? That's called caustics. Light comes through, and it bends through the curved surfaces, and they collect. The light intensity collects in a particular area, create this beautiful effect. And it does it all naturally using ray tracing. This is called subsurface scattering. Light goes into a material. It goes into the surface, goes underneath the surface of the material. It bounces around, and it comes back out in all kinds of angles, different than the incident angle of the light. And so as a result, it looks like jade. It looks like gummy bears. It looks like jade. Milk has that effect. The human skin is not brown. It has subsurface scattering. This is what subsurface scattering looks like with ray tracing. You ready? Okay, so this is before. Oh. Yummy gummy bear. Not so yummy gummy bear. Yummy gummy. All right. So all this technology, all this research is so that we can make yummy gummy. But as a result, computer graphics and computer-generated images can be completely photoreal. Let us show it to you now. Jeffrey, he's going to show you the work that we've done with a partnership between us and Industrial Light and Magic and Epic. What you're seeing right now is completely done in real time. This is not a movie. This is computer-generated images in real time running on 4 voltas.
If you ask me, who's ever in charge of this place should be transferred to Hawk. What?
That's okay.
You think she heard us? At least we blend in for once.
NVIDIA RTX technology. Okay, so hey, Jeffrey, let's quickly go through this one time. So this is all completely in real time, as you know. This is a technology called area light. Light is coming from every single direction. It's very hard to do. Notice the shadows, notice the light. Go ahead.
Yeah, we're changing the ambient lighting right now. You'll see on the reflections, on the helmet, on the shoulders, that it changes with the light source.
Hey,
And-
Jeffrey,
Yes.
can you hear me?
Yes, I can hear you.
Okay, so I just want to let you know that unfortunately, because I took too much time, you don't have any time.
Got it.
Okay, so it's my fault. It's my fault. 不好意思。可是你比较快一点啊。
没问题。
Nobody's watching. Don't worry. Okay, go. All right. So notice. Look how beautiful the light is. Look how beautiful the shadows are. They're not all crunchy and it looks fake. Look how soft it is, and it's all dynamic. And the shadows are automatically cast on top of each other. Okay, let's go somewhere else. This is fantastic. Let's see something shiny. All right, let's add a new character. Add Phasma. This is all completely in real time. Now look at Phasma. You could see the reflection of Phasma on Phasma. And all of this is the stormtrooper's boss. Her name is Phasma. And so let's go down the elevator. Look at the reflections. Look at the reflections. All completely generated in real time. This is the power of ray tracing. You don't have to trick the computer graphics, but you have to create a brand new technology. Literally took us 10 years to do this. Look at this. Incredible, right? What video gamer doesn't want this? But with this technology, we could revolutionize the way films are made, okay? And so how about let's stop the elevator, let's go to the engine room. Why don't you walk out? Did you see the door open? The door open on her chest? All of this is being generated in real time. The parts of the surface of Phasma where light is absorbed, it absorbs it. Where it needs to reflect, it is reflected, and wherever it's refracted, it's refracted. The materials on the ground, notice, is less shiny, but we can make it shinier. Incredible, right? Ladies and gentlemen, NVIDIA RTX. Okay, good job, Jeff. NVIDIA RTX. For the film industry, we've now created this entire software stack so that it can run and synthesize film for these billions and billions of images that are being created. And so let me show you what that looks like. On the left, traditional CPU farm rendering. On the right, NVIDIA RTX. Until now, it was simply impossible to use a GPU to render the image because the images would simply not be as fine and as beautiful as software running very, very slowly on CPUs. And for the very first time, we can create images that are completely photoreal and yet is completely accelerated. The benefit is to the customer. So good. Traditional render farm, 280 servers, accelerated render farm. The more you buy, the more you save. That's right. Okay? So go and tell all your friends, the more you buy, the more you save. This stack, remember the basic equation. We create the architecture, the acceleration stack, in this case, the RTX technology. We work with all of the software developers from Pixar's RenderMan to V-Ray to Clarice to Arnold. And then we have a team of technical experts in the ecosystem in the world working with all of the leading publishers and leading developers and filmmakers to create their film in the future with this accelerated stack. And everybody loves saving money. Nobody I've met doesn't like to save money. Saving money. Enormous industry. Today, completely using render farms. In the future, could be accelerated. And the more they buy, the more they save. A new industry we're going into. This is the work of almost a decade as well. For a decade, we've been working with the medical imaging industry. The best way to extend life is to detect a disease soon. And medical imaging is the fundamental and the essential tools of doctors. There's all kinds of medical imaging approaches. There's PET, there's MRI, there's CT. MRI is good for soft tissue. CT is good for bone structure. You have ultrasound, of course. All of those methods, working with the leading medical imaging companies, from GE to Philips to Siemens to Canon in Japan, we have been working with them over the last 10 years to put computational methods and CUDA GPUs inside their instruments. The latest generation Philips ultrasound, incredible technology, has CUDA inside. GE's Revolution, this incredible MRI machine, CT machine, has GPUs inside. And so we're computationally accelerating medical imaging. However, in the last several years, advances have moved so fast, and there are millions of medical imaging equipment around the world that unfortunately will take decades to upgrade. And so what we decided to do is create a virtual remote supercomputer. It sits in a data center, or it could eventually sit in the cloud. This data center will run the entire software stack of a medical imaging system. From from reconstruction to applying AI for detection to visualization, we virtualized the entire software stack, and we created what we call Clara, and this will just run in the data center. And so you have the GPU server, the containerized and virtualized software, all of the APIs and acceleration layers, and the software that goes on top of it. Let me show it to you. On this side, what I'm showing to you is this. The input for both of these sides, this is traditional MRI machine running a filtered
backpropagation. Or projection, sorry.
Okay, and so is it projection? Filtered back projection?
Yes.
Okay, so this is a traditional technique for filtered back projection. It assumes that your body does not attenuate X-ray. But that's not true. The way that they solve this problem is simply to increase the dosage of X-ray so that your body does not attenuate the signal, and so that they could collect the back projection and reconstruct the image from it. This is a technology called iterative reconstruction. This doesn't assume a particular model that computes an X-ray model called radon model. This doesn't assume that. This iterative reconstruction method, one beam at a time, calculates, estimates, and corrects, and over time creates this. It's essentially the ray tracing, if you will, of medical imaging. And it computationally is several hundred times more than the traditional method. This is what's inside today's CT machines, except for the latest generation ones. The vast majority of the world's CT machines like this. If we could use this technique, iterative reconstruction, we could reduce the dosage of X-ray tremendously while increasing the resolution and fidelity of the reconstruction. And so what we're seeing here is simply this. What goes in is a sonogram, which comes out of a CT machine. The raw data of the CT machine comes out. It goes into this Clara server. It runs a piece of software called Astra. Astra is running filtered back projection, FBP, and this one's running iterative reconstruction, IRT, okay? And so let's go ahead, Mike, fire it away.
All right. So we're just going to go ahead and launch this since it's already been set up. But what you're going to see here on the left versus the right is the CPU versus the GPU reconstruction. And this is all happening within the browser. And as the layer is calculated, you can see them start to come back in.
So what's happening here, as you know, this side is doing 400 times more computation than this side. And it's doing it faster. This side, running on GPUs, is running several hundred times more computation than that. And look at the results. With the same amount of input from a sonogram, you could create much higher fidelity images. The other way to think about that is this. If this is the level of fidelity that you're comfortable with, you could reduce the amount of energy dose by a factor of 6. Another way of saying it is this. We can now use CTs for even children. Today, you can't use CT for children because the X-ray dose is too high. So the opportunity to be able to use medical instruments with computational advances is really quite groundbreaking. That's why GE calls this particular machine with IRT revolution. Okay, so now that we can do that, but we could do so much more. This is what the old machine looks like. Now that we can put this on Clara, we can apply AI to it. And so what Mike is doing here, he's applied this neural network that has been trained to detect organs volumetrically. We trained this neural network called VNet to detect 3D volumetric organs. I don't know any of the organs. Okay? And so now we could use AI to train the organs, but it still looks kind of difficult to understand. So we could now apply ray tracing to render this image. All right, you guys, look at this. Are you guys ready for this? Before, after. Before, after. Okay? Without, with NVIDIA acceleration. Okay? Wow, 好漂亮啊. Okay, good job, Mike. Thank you. So, $7 trillion healthcare industry. We've now created a computer for healthcare. You could use it for imaging. You could use it for genomics. You could use it for AI. And it sits in your data centers, virtualized. We've turned healthcare, revolutionized it with modern computing. Once again, a fully accelerated stack, special libraries, working with the application developers in each one of the industries, and having a technical team developing it with partners. Safe city, same strategy. Billions of cameras will monitor public spaces in the future. Keep us out of harm's way, keep traffic moving, figure out where the energy density is the highest, and divert energy from the energy grid. And as a result, we could create safe city using exactly the same architecture. However, we need a specialized stack. We have a DeepStream SDK. The DeepStream SDK takes video from hundreds, thousands, and in the future, millions and billions of cameras. Comes in, it has to decompress it, do image processing on CUDA, run inferencing on all of these different types of networks, and whatever networks comes, and then pass the metadata to the VMS, the video management system. And we work with a technical team, work with developers all over the world as they create smarter cities. $2 trillion smart city market. Everything in the future that moves will be autonomous. AI is the single greatest contribution for autonomous vehicles, in my opinion, is the single greatest contribution we can make to humanity. Safer roads, reduce the cost of transportation, reduce traffic congestion, keep people out of harm's way, save lives, and not to forget that 1 billion people are going to come into the world soon. 1 billion more people. And because of our online shopping habits, the Amazon effect, we have so few truck drivers now. There's a great demand for truck drivers as we all want everything delivered to our house instantaneously. We want Nero Mien delivered to our house. We want a television delivered to our house. We want Youtiao delivered to our house. Incredible. And so the number of truck drivers, the number of drivers in the world simply can't keep up with that. And so we believe that the answer is using AI and create an autonomous computer. This computer is a one-of-a-kind type of computer. We created, of course, the driving car computer, and I'll show you that in a second. But the way I mentioned, the software development of the future is fundamentally different. The software development methodology of the future is fundamentally different. You're collecting an enormous amount of data. In our case, we have test cars all over the world. We collect a few petabytes of data per car from all of the sensors per day. We then run an artificial intelligence network on our supercomputer to figure out which one of the images we should label. We then take the output of that AI and we took it into a label factory, data factory. People that are just precisely labeling, identifying the objects inside the images. We then have a deep learning team with their supercomputer, and this deep learning team is creating new artificial intelligence networks and training the networks. And then After you're done developing the software, of course, you have to simulate it and you have to test it. The world drives 10 trillion miles per day. Okay? And so the world drives a lot of miles. However, the best we can do is to simulate, to test our cars, if we're lucky, millions of miles. And so we need to find a way to simulate 1 billion miles or so inside virtual reality. And as you know, we have the technology to do that. So simulate and testing, and then that results in a drive computer. The drive computer looks like this. Hey, Paul. Drive PX Xavier. Okay, so this is a future drive computer for an autonomous car. And so if you have a branded car, it would have a computer like this. This chip is called Xavier. It's the largest SoC the world's ever made. And this computer has 2 Xaviers and 2 Voltas on there. And this is going to be a driverless taxi. These 2 architectures is exactly the same. Okay? And so as you can see, this motherboard, this computer, goes into a self-driving car. There are going to be hundreds of millions of cars in the future that are going to be powered by this. 100 million cars made each year, trucks, shuttles, and then, of course, in order to develop the software for it, give me the HGX2. Yeah. No, give it to me. Kuaidian. Okay. All right. Ladies and gentlemen, this goes into the supercomputer here for training and for simulation. And then when you're done with the software from here, you put it in here and you put it in the car. Does that make sense? Okay? One architecture. The software that runs here and the software, binary compatible. Incredible, right? Wow, 好重啊. Okay. All right. Okay. Can you do it? I bet you can't do it. You're not strong enough. Not like me. Okay. All right. And so our engineers are developing all the software from beginning to end and all the driving software that runs on that car. We have hundreds of partners now all over the world. Let me show you. Every time I come, I show you the latest update of our car. This time, you will notice the 3 stages of autonomous machines: perception, reasoning in the case of a car, localization, and then action in the case of a car, path planning, driving. Okay? Perception, localization, and planning. You will see that we use camera. We will also use LiDAR, and as we go across these 3 different ones. There's one more thing that we will show you this time, and that's the car is going to create its own map. You know, when you visit a place the first time, you're a little bit not very confident. You're not sure where everything is. But the second time you come, you're very confident. And the reason for that is because you created a map in your head. Our cars are going to do the same. The first time you drive a new place, we're going to create a map. The next time you come back, we're going to use that map along with everything around, all of the other algorithms I described, to enhance your safety. Okay? And so mapping. And then lastly, I'm going to show you for the very first time, location to location driving. Okay, let's fire it up. The car has so many different neural networks. We're already up to 10, 12, or something like that. We'll have 20 before the end of the year. Any weather condition. Figuring out where all of the other cars are, called lane assignment. And does lane assignment and surround. LiDAR object detection and perception. It's now mapping. Using visual odometry, basically a camera only. We can map with camera and LiDAR. The AI is also watching inside the car to make sure that you're not falling asleep and that you're paying attention. This is Janine, one of our employees. Now the car has mapped, and we're going to use that map to drive by itself the second time. It's came out of our company, stopped at a red light, stopped at another red light, made a turn all by itself. It's going to go on top of no HD map at all, completely mapped by the car. Goes on a highway. No LiDAR, no HD map. Ladies and gentlemen, the future of autonomous vehicles. And so first of all, the important thing to realize is there are probably going to be 150 million cars and taxis and shuttles and trucks and vans and buses that are going to be autonomous each year. Okay, so we're going to build a lot of autonomous vehicles. However, the thing to realize is the software needs to be developed. And every car company will have supercomputers in the future. And these supercomputers are one of the HGX or HGXTs or HGXIs or the sexies. Okay? And so there are going to be different classes of computers used by different phases of developing the software. But there will be billions of dollars of servers. Billions of dollars of servers that will go to car companies all over the world as we all develop autonomous driving software. NVIDIA's platform is open, and that's one of the reasons why there's so many companies who are working with us. Let me show you one more thing. This is really fun, and I want to expand your horizon. I showed you this at GTC, and basically it's called Project Wakanda. Let's run it. Just keep running it. This is Project Wakanda. You go into a holodeck, you sit down, holodeck creates a virtual reality car around you. Inside your holodeck experience, you see the world outside. You see out this window. You see this truck right here? It's right there. Can you guys see that? This person is inside our company in a holodeck. This car is not driving by itself. It's driven by this guy in holodeck, just like Black Panther. Okay? That's why we called it Project Wakanda. Can you guys see this? There's Tim driving the car in virtual reality. He sees everything, steering the car. Look how accurate he can steer the car. Oh, come on. Get it parked. Oh, look at that. Oh, perfect parking. Completely remotely in virtual reality. Okay? Guys, we call that Project Wakanda, but we brought it to Taiwan. The thing that I wanted to do is this. You know Black Panther, Project Wakanda, you guys know, right? Okay, imagine you're Black Panther, but we took it into Ant-Man. Can you imagine this? Black Panther, Ant-Man, the two movies come together. Justin calls this Project Wakanda. Small. Wakanda. I want to show it to you. Are we going to be able to show it to them?
I think so.
You think so?
I think so.
You think so?
Yeah,
you hope so?
It's totally
okay,
live.
ladies and gentlemen, so. Project Wakanda. Little tiny miniature. Okay, so there's Justin right in front of you. He's in virtual reality. Here's Justin. Ladies and gentlemen, Justin Ebert. He's driving this car in virtual reality, okay? But watch. Look how small he is.
Remote driving activated.
Okay, so, he's gonna. Yeah, go ahead.
Yeah, so actually I'm on the top of this building in a small car. And we built a little mini city here, and we've got a little tiny quarter-scale car that we're
Can you see
controlling.
this? This is what Justin sees in his virtual reality world. He's sitting inside a virtual reality car. Outside the car, he sees all this. And you see all those guys up there? He's a miniature car.
So I think somebody needs to activate me
Okay.
because I'm unable to drive. Let's see if I can.
Can you drive?
I would love to drive.
You,
There's nothing I would love more than to drive right now.
no, apparently, the
Oh,
reason...
I'm dumb. Look at me. I didn't put it in drive, so I think that's what I did wrong. Hey, there we go. Yeah, there we go.
Can you see him? All right, what is the application for this? Well, in the future, as you know, we're going to have a bunch of little tiny pizza delivery things, right? But sometimes they're going to get stuck. So we will be in virtual reality and we will go into that robot and we will help the robot get unstuck. If you have a driverless taxi, there's nobody inside that car. If something happened and it gets stuck, we can go through virtual reality into that car. In the future, if we make robots and the robot is guiding people from in your hotel from place to place and it gets stuck, you can go into the robot and you can navigate the robot. In the future, if you want to have telepresence, meaning you're in Taipei, but you would like to attend a meeting with me in California, and you would like to sit virtually in the conference room, you will go through virtual reality into that robot, and you will sit there, and you will look around just like this. And maybe the glasses are even very, very small in the future. In the future, you will be able to merge with a robot. Hopefully the robot is an attractive one, but you will merge with a robot. You can have telepresence. You can go anywhere you want. Right now, Justin is upstairs, but he's not upstairs. He's right there. But he's enjoying upstairs, like controlling that car in virtual reality. Does that make sense? The future of virtual reality, telepresence, and autonomous machines are going to come together in a new way. And Project Wakanda was to explore that. This is just to expand your horizons of some of the things that we're working on. Justin Ebert, thank you very much. Guys,
Thanks, everyone.
Ryan, Jeffrey, Mike, 光临，谢谢大家，谢谢。So that's it. Moore's Law has come to an end. We need a computing approach going forward. If we just consider that applications will continue to grow in demand exactly in the same trajectory, we will need, in just 10 years' time, in the year 2028, we will need to deliver in the industry 10 million Volta equivalent GPUs. Incredible amounts of computing. But yet, I believe that computing, because of AI, will write larger software, and we will need even more computing than that. GPU computing, it starts with a great chip, and we created this new chip, new processor called Tensor Core GPU. But that's just the beginning. What accelerated computing is all about is full stack. So creating a new type of processor that fuses HPC and AI. Number two, optimize across the full stack, developing switches, developing motherboards, developing systems, system software, APIs, and libraries, full stack. We have now reached the critical mass. Every developer in the world who needs more computing has jumped onto GPUs. This is how they're going to do groundbreaking work. 850,000 developers around the world, 550 applications have been accelerated. Literally every single leader of servers has adopted our architecture, and I want to thank you all for that. HGX2, Foxconn, Inventec, Quanta, Wistron, so many others. We are working with literally the entire computer industry because everybody needs a solution forward. Everybody understands the importance of AI. It's going to be the future of developing software. Delivery of the software is complicated. We created a cloud of clouds, a registry we call NGC. All of the acceleration stacks are there. And great computers and great platforms need applications and need demand. And now, with all the work that we've done over the last 10 years, one domain after another, one vertical after another, we create proprietary, specialized software stacks that accelerate the most important applications in each one of those verticals. AI for training, AI for inference, CUDA for high-performance computing, supercomputing, Drive. That entire server has a reference design called training, simulation, testing for autonomous driving and infrastructure. I call it Tostada. If you can't remember what this is, just say Tostada, and NVIDIA salesperson will help you. I would like to have Tostada, and then they take you to a Mexican restaurant. And so each and every one of these vertical markets, $1 trillion of vertical markets, can now be served by GPU-accelerated computing. I want to thank all of you for all of your support and all of your interest in the work that we do. The future of computing is rich with opportunities. This is the beginning of a new revolution. I want to thank you all for being here today. Have a great GTC.